Don't forget to leave your thoughts about our speakers in the DSS app. We appreciate your feedback, and so do the speakers. In the console, you'll also be able to join our community Slack channel. So if you haven't actually done it, you should do it now so you can have a better conference experience overall. There's a lot of great discussion going on so far, so jump in. We'll keep the networking going today after the event at 4:30 p.m. Eastern, 1:30 Pacific, with our Tuesdays together in the Snack channel, club channel that I mentioned earlier, where you will be paired up with another or several other people who are attending this conference, and you will be given some ice-breaking questions to start the conversation. And it'll be a really nice way to meet other people and just kind of continue the groove since we can't be together in person. Next up, we have Abhishek Mehta, Director of Field Engineering at TigerGraph, and Gaurav Deshpande, VP of Marketing at TigerGraph, and they will show us how to double the performance of your fraud detection system with the Graph DB and machine learning. Cool, I'd like to see that. Submit your questions into the panel, and we'll go over them right away, and whatever we don't answer, we'll go right into Slack. So thanks for being with us, Abhishek and Gaurav, and please take it away.
Hi, everybody. This is Gaurav Deshpande. I'm the Vice President of Marketing with TigerGraph. And with me, I have Abhishek Mehta, the main man, who's going to walk you through how you can double the performance of your fraud detection system with graph database and machine learning. Let's go to the next chart. So a little bit about who we are. Who is TigerGraph? We provide advanced analytics and machine learning on connected data. So if you remember one thing about us, that's the thing to remember. We are the only scalable graph database for the enterprise. In fact, we are 40 to 300 times faster than the competition. We are foundational for AI and ML solutions for multiple Fortune 500 companies. Our customers include some of the largest companies in banking, in healthcare, telecom, media, utilities. And for today's session, which is focused on financial services and technology, I'll cover those references in just a moment here. We were founded in 2012, about 8 years back now. We are cloud neutral, which means we support all 3 clouds, and we also have several on-premise deployments for our larger customers who choose to do it that way. Let's go to the next chart and look at how customers define us. So this was actually came out of a customer advisory board session that we did. First and foremost, we are a distributed graph database. When you look at that, the thing that we are doing there is we are connecting all your data sets and all your pipelines. 3 customer references there: United Health Group, which has created a customer 360 by connecting over 200 different data sets and pipelines. A large Fortune 50 retailer that has integrated 100 different data sets to build an item 360 for e-commerce. And AT&T's Xandr unit, XANDR, which is their advertising technology unit. And they have built an identity graph connecting about 50 data pipelines. The second component of TigerGraph is advanced analytics. And there we have a couple of examples here. After you have connected the data with the graph database, we are analyzing that connected data. There we are about 10 to 100 times faster than the current solutions. An example here of Jaguar Land Rover, the famous automotive manufacturer. We took the supply chain planning from 3 weeks down to 45 minutes there. We also have the example of China Mobile there, and we do it for several other companies in banking, in telecom and technology, where we do fraud detection, move the fraud detection from batch to real-time fraud detection. Last component, the third component, is in-database machine learning. This is where after you have connected all the data sets with the graph database, you have analyzed it with advanced analytics, we are doing the third part, which is we are learning from the connected data. I've given a financial services example here. We are doing this at multiple banks. In fact, 7 out of top 10 banks in the world use TigerGraph for doing fraud detection and credit risk assessment, and all of them are learning from the connected data. Intuit is, of course, the parent corporation of TurboTax, and they have built an AI-based customer 360 for entity resolution, recommendation engine, and fraud detection. With that introduction about Intuit, let me hand it off to Abhi, who's going to talk about how you can control fraud detection and double the performance of your system in financial services and technology using TigerGraph.
Great. Thank you, Gaurav. Hello, everybody. Abhi here. So let's put this whole fraud detection problem in a business context first. So what are the business drivers behind the continuous investment in graph databases, machine learning, and data science team when it comes to the fraud detection world? So the biggest driver here is that there are $30 billion losses worldwide on the fraudulent transactions, right? And above that loss of money, one out of the 5 block transactions are actually fraudulent. So technically, we are having 4 false positives for every transaction, what we mark as fraudulent, what we find as fraudulent. And that leads to a huge revenue loss when you realize that 40% of the denied users are actually trying to put transactions which are over $250. So they're having false positives is a huge loss of revenue for all the customers or all the merchants or all the vendors supplying that. And again, there is a high income factor to it. I mean, those who are doing these kind of transactions are often high income group customers. And of course, there is a profiling angle to it, that there is certain age group of people who are less than 35-year age, more susceptible to be misidentified as doing fraudulent transactions. So when you put all these points in context, it makes a lot of sense for financial institutions to, rather than hiring fixed cost analysts to keep on analyzing each of these transactions and manually marking it off, to employ smarter, intelligent AI, machine learning, data science technologies to find out fraud, increase customer satisfaction, and of course, cut down on the false positives that we are seeing here. So our whole conversation is going to revolve around a very basic use case, which I'm going to flowchart over here. So let's define the semantics of this use case first. So we may have done this use case in the morning today. We all have bank accounts. There may be savings account. We may have checking account, maybe credit card associated with the bank. And these accounts have our phone numbers and email and some other PII data. Now, if you do any payment, any transactions, so technically you will be using some sort of a device. And now, by virtue of this action, the bank knows the device which gets connected with your account. So when that happens, what it takes 2 to do a transaction. So there has to be another account on the right-hand side, which we have, and that is associated with the customer. And if you look at the customer, same way what is on the left-hand side applies to the customer on the right-hand side. They may have used some phone number to authenticate. They may have used different devices. So this is how this whole network of charts spans out for a very basic use case of we having account and doing a transaction. Now let's look at this scenario from the right-hand perspective, where we have marked everything as red. Let's say there is a device used with this phone number which was marked as fraudulent historically. Maybe just by the phone number, maybe the device ID, maybe the payment was tagged fraudulent. So it could be anything. Now, technically speaking, if I did a transaction this morning using my account with such kind of account which has associated with fraud in the past, my transaction should be marked, or at least red marked, for analysis, that why is this happening? There is some angle of possibility that this transaction is fraudulent. Now, when we span out this kind of problem on the chart, it's very easy to understand, because just by virtue of what I've marked this as red over here, it is very clear to us that why is my transaction marked as fraudulent. This is easier said, drawn, than done. Now, let's look at the implementation aspect of this in the RDBMS world. RDBMS Look-alike for this thing is going to be some sort of normalized schema. Or maybe, look-alike, what I mean is also that you can look at some NoSQL, but nobody uses NoSQL to do transaction processing. So in that aspect, let's focus on RDBMS. And let's say if we were modeling the solution, 2 tables you're going to focus on is transactions or your user data, whether it's data coming from your data lakes also. These are the tables you are going to focus the most on. Because to find a transaction done by a user, the devices he has used, you have to go in and out multiple times of these tables, creating self-referential joins. And that is going to complicate the situation so much that if you start putting some kind of decaying factor of finding that, okay, maybe I'm not transacting with one fraudulent user, maybe that user is transacting with a user user down his own transaction, and that user down his own transaction, and you want to find out the chain of events which occurred before you find a fraudulent transaction with my transaction overlap, it is going to be a nightmare to implement such kind of solution on RDBMS. It's just not technologically feasible. And if you try to make it feasible by complex SQLs, you would see that your cost of ownership, the kind of hardware and licensing you would require, becomes extreme. It becomes almost unbearable to have that kind of flow, that kind of output, exposure of hidden patterns inside your data set. So that's why we often call that connected data is a graph problem. You know, when I was discussing this diagram with you earlier, I was saying that, okay, let's chart it out. Now, what I would tell you is this is exactly the data-centric view, how graph databases store the data. This is exactly how the data is stored inside graph database. Let's focus on any of the circle here. They are called vertices in graph database. You know, let's look at the payment. Now, technically, payment is only one hop away from the account information of the receiver and sender and the device which has been used to make this payment. So you don't have to go into any different tables or different kind of, ledger kind of look rows and columns. All you need to do is traverse one hop, and you know all the entities that are linked with this particular payment. Similarly, if you go to an account, you would find out one hop away all the payments that that account has been utilizing, and which can be used to find the shortest path and interlinkages and calculations based on all these entities we have. So I'm going to very quickly switch on to our demonstration of the product so that you can understand it a little bit more deeply. So I am taking you to Graph Studio right now. TigerGraph has, this is our visual SDK. There are various different possibilities also. You know, we have RESTful APIs, we have CLIs, we have various different connectors. So just for ease of understanding, right now I'll be focusing only on the use case here. So under the design schema, I have exactly mapped the RDBMS model onto a graph model. That's just for ease of understanding. You have a user, you can see their attributes. You have transactions, they have their own attribute, timestamps, amounts, payment instruments, and they have their own attributes. So this is a very basic model of how you would map the schema inside a graph database. So let's move on to what I have in this data set for you. So there is a preloaded 1 billion vertices, 4 billion edges, some 800 million transactions in this system. So this is something in the range of 100 to 200 gigabytes of data sets imported inside TigerGraph. And these billion entities is a mediocre system. You know, if you want, our system can scale up to trillions. We have customers already in production doing that. So let's look at this use case. The data is preloaded. And first, let's see why the storage of data inside Graph is so different from RDBMS. So in the exploration, I'm just picking up 5 random users. Let me show you all one-hop neighbors, what can be accessed from this data point of this particular user. As I double-click on it, it's just not about pretty visualization. Visualization is just a byproduct of TigerGraph Graph Studio. What you're seeing is this user has done so many green transactions, and he has used various different devices, 1, 2, 3. Now, who used these devices? Who else used these devices? Let me show you. There are 2 other users that use these devices. So just by keeping the schema in mind, all these users should have their own transactions and devices. Here we go. They have their own transactions and devices. And this transaction should have been with another user. And this user will have its own device, its own transactions. So it's not about just the pretty visualization, as I was mentioning earlier. It's about finding these linkages between this data set that connects data-centric view, one data point to another data point, just by navigations of these relationships between them. That's what makes the traversal over billions of records so simple and so easy. What can you do with this? You can do very smart graph algorithms. So I will show you a very basic one. So right now I'm going to find a relation between a user over here on the left and a device here on the right. I'm going to wipe this slate clean. Now find me one shortest path between these two users. Let's expose a hidden pattern inside this data set. Up to what depth are these guys connected? And here you go. In matter of milliseconds, sub-second query response time, I'm able to show you a path. TigerGraph's MPP architecture, plays a very smart role over here. The sharded data sets that this user, which I gave in as an input, and this device is connected by a user referral via a device, via another user device, and a transaction between this particular device using the central user. So whole of this correlation, the exposing of this hidden pattern is virtually impossible to achieve in RDBMS. Means I don't want to overstate this, but the fact is this kind of depth, 1, 2, 3, 4, 5, 6 hop analysis is extremely complicated on the schema that I was showing you earlier. Now, this is a traversal path. Now imagine this being used as a feature or a circular query inside your own machine learning and graph models that you're creating. Let me show you what more smarter things you can do on it. There are various different ways. What you're looking at is a GSQL query, writing your custom logic, which is all parameterized, and it is trying to find out that if when a live real-time transaction is happening, giving a random transaction, there are two users associated. Those users have their own devices, and all those devices were used by many other users, and those users have their own devices, and they are being used by many other users. So I'm creating clusters on the left and right side of this transaction and trying to find out that is there an overlap of money transferring from one cluster set of users to another cluster set of users. Maybe I want to do this as an anti-money laundering scenario, and trying to find out money laundering scenario and trying to find out this correlation. So billions of records, folks, as you have already seen, you are aware of the schema, and here we go. This is the sub-second query, just not a pretty visualization, as I mentioned 3 times already. This is my transaction. This is the two users doing the transaction, and there are the clusters of their users based on the devices they have used. And we are finding one overlap right here in the middle. So up to a 5 hop down based on the devices, there is one transaction which is overlapping. Now, transaction can be a big amount, it could be a small amount. You can have aggregation on top of it, whichever way you would like. But the nutshell, the idea is ability to expose these kind of patterns, these kind of calculations, these kind of sorting, aggregations, basic data science operations, and I will show you advanced ones also, gives graph database a huge possibility to be used inside the fraud detection scenarios. Let me take you back to what we was showing you earlier onto our presentation. So what happens with these possibilities? What are the possibilities of a system that can traverse the data so smartly, that can calculate and compute parallelly on all the nodes that you find, whether it's about aggregation, summations, or all the things that you're trying to do, or running some basic algorithms or advanced algorithms? What are the possibilities for machine learning, AI, and a data science team? The biggest use case what we are seeing is ability to extract smarter features for your training set, for your model training. Here is an example. On the left-hand side, you are seeing your good old RDBMS schema. On the right-hand side, we have our graph schema. So what's happening over here? Let's say you want to calculate total value of all transactions of a particular merchant. Remember, as I was doing on a payment, when you hit a user account from a single hop, you can get all the payments which that account has made. Similarly, from a single merchant account, now you will be able to access all the transactions which may run into millions based on a time window for a merchant, and you can aggregate that. The aggregation is also very fast because of the MPP architecture, and also the traversal is extremely fast because you're not cutting through any rows and columns and tables and making self-referential joins. It's just about hopping the memory locations. On the second aspect, there are various different features that you can extract out of this. For example, amount of transaction. This is summation. A maximum value of a transaction. This is more of finding the highest value. Sorting the top 5 transactions. That could be ordering mechanism. So as I was saying, all these functions can be done with sub-second time on the graph databases, which may take long time to run on your Hadoop clusters or your data lakes or your RDBMSs, even in Spark, because the challenge at Spark is that data sets which are once loaded cannot be modified, and if the data is changing in real time, your options are very limited over there. So that's the biggest feature in which the graph is being used in ML and AI world. The TigerGraph provides you with all the capabilities of Python wrappers. We have JDBC drivers, Hadoop connectors. So all those possibilities merged together makes a wonderful system. And here is an example of such a wonderful system, right? We have a top tier US bank using TigerGraph for on 20 terabyte set of credit card data. They have used the 6 weeks of POC, and it took them 3 months of development to take them into a platform to production. And this production, depending on how do you take things into production, could very well be pre-production, right? The testings have to be performed with the 16.5 million first year ROI with 30% uplift in fraud detection. The whole idea here was to detect use feature extraction of this 1, 3, 4, 5 hops and doing it in real time. Their response window time was extremely short, anywhere from 30 to 50 millisecond on 20 terabyte of data set. So they created a 10 machine cluster, which of course had replication and high availability to achieve what is now a big money saver for this bank. Now with that, let me give you another aspect of graph databases, and that is related to graph algorithms. Now, when you store your data in graph structures, as I was showing you earlier, you open yourself up to various different possibilities which were not possible earlier with the two-dimensional data structure. Example being, now you can run page ranking algorithms on it. Now you can run some label propagation algorithm. You have already seen an example of shortest path between them, community detection, similarity detection. So all these algorithms are now possible, and using TigerGraph means you can run those algorithms in parallel. Some of the algorithms are compute intensive. Some of them earlier used to take days. With TigerGraph can be done in hours on terabytes of data set. And I'm going to show you one such example right now. Well, I will be telling you more about it. So this is a hottest thing inside fraud detection right now. When I say it's not about detecting just the fraud rings, it's about implementing two smart algorithms together to detect the communities of either fraud rings or targeting them for sales and marketing. It's more about community detection. So the use case here is that you have huge set of credit card information. Some of them are merchant data, account information holders, or credit card holders, and the transactions between them. Merchants have categories, hundreds of different attributes, geolocations, and all those details. And a very tiny little set of data is about fraudulent transaction inside. So it's more of an unsupervised way of finding newer fraud rings. So the very simple logic here is, conceptual logic here is that if I have right in my area, there is a Rite Aid and there is a CVS across the road. So a lot of our people in the community will go to CVS and Rite Aid on specific days. So just by the density of users between two vendors, we can connect these two vendors in just based on the credit card holder activity. That those people who transact at CVS also transact at Rite Aid. So if you make this correlation between the vendors, now you can run page ranking algorithms. Based on various different criteria, you can rank the vendors overall based on a state, based on a city, based on any criteria of earning possibilities, and based on various products what they sell. And now you have this page ranks. How about running a community detection algorithms to detect hundreds of thousands of communities to hundreds of communities, whichever way you want to detect. All the people who sell the same product, all the people who have price range average sale of $20, $30 or per transaction. So once you detect these communities, your fraudulent, whether there's a device fraud or your fraud rings, this tiny data set will fall into these categories. there will be a fraudster who will be falling into these specific categories. So with the PageRank, you equip with PageRank, you equip with communities, hundreds of thousands of them, you can rank out the top communities, since they are very tiny communities, because you have done 100,000 community detections, very tiny communities of users who are having maximum penetration of your known fraudsters. So technically that might be a fraud ring operating out of those communities. There is a possibility that that is a high value target for you in terms of putting your sales and marketing dollars if you're looking for on product sales. So there are various different aspects. You can join these things together. You can rank them by the average page ranks and make sure that you look at the highest value communities based on page ranking, connectivity, or things more details like the fraud rings. So this is a very strong use case, making very popular financial institutions. We have made many sales around it. Well, that being said, let me show you quickly what are the very quick other possibilities, just not the fraud, credit card scoring, wealth management use cases, trade surveillance, impact analysis, merchant analytics for finding the right communities where based on the patterns of how the people buy. It may be a mall because everybody who transacts at Panera also goes to Macy's, also go to Nordstrom. So there is a huge enough pattern to detect that these merchants are probably geolocationally co-located. So with all those kind of details, there are various different use cases which emerge out of graph databases, possibilities for you to respond back in a matter of milliseconds and run these algorithms at scale in parallel. With that, I will quickly show you our differentiator from the respective computation what we have. We are a native parallel graph, and we are a distributed graph. So we shard your data. We store it on lower cost servers. You can have high computation based on the cores are available on it. Your cost of ownership goes down, and we can execute your queries in parallel. So the hours of work can be done in a matter of minutes. So we scale up and out both. You can have high-end machines, or you can have cheaper machines to do the same operations quickly. So cost of ownership, as I earlier said, can be low. We have enterprise features. All these banks are using us, so we fit into their operational and non-operational requirements with high availability, security, API integration. I showed you GSQL, which is built ground up for performance, for distributed performance. And similarly, deep link analytics, I showed you 510 hops, graph algorithm libraries. We talk about community detection, page ranking in parallel, multi-graph, Graph Studio. And one thing which is not to be missed is that we are ACID compliant. So technically, we fill in that space of a database, which is both OLTP, transaction processing, and also OLAP, analytical processing, all in a single platform. So that is a differentiating factor of TigerGraph from what that exists in the market. We are very proud of flashing this, means happy about it. Now, if you want to get started with what I have been showing you here, or what I've been telling you about, you have 3-4 different options. You can either use our TG Cloud. I will recommend you go to tgcloud.com, create a free account, and all what I showed you is available there in our starter kits. You can just trigger a free instance. You can load a starter kit, which will give you all these use cases that I was showing you, and you can run and see and modify the queries. Or you can download our free enterprise edition up to 50 gigabytes. There is no licensing cost for you to use TigerGraph, so please download the version from our website. Also, you can go into our tigergraph.com under Graph AI World. There are 40 plus on-demand sessions which have been done by all these names, what we have taken over here as our panelists, as of their own webinars, telling about how they solve their problems on graph database, which is TigerGraph mainly. And also, you can take a test drive, which I was demoing you, where you have billions of records to test the use cases, including anti-money laundering scenarios like entity graphs, also marketing analytics. And last, I will recommend you to join us on our community, tigergraph.com. It's a big initiative where you can learn, ask questions, and there are a lot of people to help you out along with our open source community.
Thank you so much for that presentation. Really enjoyed that. We only have time for just one question. So I'm going to ask that question right now, and the rest of the questions we could take into Slack. So this was a good one. How is TigerGraph different from Neo4j? And is your graph technology based on Neo4j? That is the question.
Wonderful question. Wonderful. Thank you, Anna. And first of all, thank you for the question. I want to say that Neo4j is a wonderful graph database. I myself learned graph database with Neo4j about 12 years back. That said, it was built for 5% of the data volume that exists right now. So, typical Neo4j deployments are between 100 and 300 GB. Our deployments go all the way from 50 GB to 22 terabytes. So, performance-wise, we are about 40 to 100 times faster than Neo4j, and we are a truly distributed graph database built from scratch. So we are not built on top of Neo4j. We are the third generation graph database that's about 40 to 100 times faster than Neo4j.
Wow, that's awesome. I didn't know that, but thank you so much for sharing and answering that question. And we're going to take the rest in Slack, and I think there's probably going to be more follow-up on that as well. But thank you so much. It was great to have you.
Thank you, Anna.
And we'll
Bye.
see the rest of you guys. We'll see everybody else on the next session.